Dear viewers, James Webb Space Telescope has made a significant observation regarding the rate of expansion of the universe, leading to a serious issue. The findings have validated the most significant problem in cosmology, known as the Hubble tension. So, what exactly is the Hubble tension, and why has it become such a significant issue for astronomers? What did the James Webb Space Telescope observe that validated the cosmological crisis? Most importantly, what new physics would be unveiled in resolving the Hubble tension? To comprehend the most significant crisis in cosmology, we need to travel back a century to the 1920s. During this time, two astronomers, Harlow Shapley and Herbert Curtis, were involved in a heated debate known as the Great Debate. The crux of this debate was the scale of the universe. The question was straightforward yet profound. Was our Milky Way galaxy the entire universe, or were there other galaxies beyond it, making the universe much larger than we assumed? This question may seem strange today, but back then, astronomers believed that the entire universe consisted of just one galaxy, the Milky Way. Of course, we had images of other galaxies like the Andromeda galaxy, but for a long time they were considered star systems within the Milky Way. Hence, they were referred to as spiral nebulae instead of galaxies. Therefore, the dispute centered on whether the spiral nebulae were situated within the Milky Way galaxy. Shapley argued that the Milky Way was approximately 300,000 light-years wide, and all the star systems were well within the Milky Way's outskirts. In other words, the Milky Way was the entire universe. Conversely, Curtis contended that the nebulae were independent galaxies like our Milky Way, located at a great distance. The debate occurred on April 26, 1920. It was a battle of perspectives where the scale of the universe and the nature of the nebulae were open questions. Regrettably, the debate did not yield any significant results. Astronomers remained divided. The answer to the question came not from the arguments of Shapley or Curtis, but from the diligent work of an American astronomer named Edwin Hubble. In the 1920s, using the most powerful telescope of his time at the Mount Wilson Observatory, Hubble made a remarkable discovery. Edwin Hubble made a groundbreaking observation when he looked at the Andromeda Nebula, once thought to be part of our Milky Way. He focused on a particular type of star known as a Cepheid variable, specifically star Vi-1 in Andromeda. His measurements revealed that Andromeda was about 1 million light-years away, triple the size of what was believed to be the Milky Way's span. This confirmed Curtis's theory. The spiral nebulae were indeed massive galaxies similar to ours. Hubble's findings didn't just redefine our cosmic map, they also introduced a new puzzle in cosmology. As he studied the heavens more closely, he noticed that distant galaxies seemed to be drifting away from us. The further they were, the faster they moved. This led to the formulation of the Hubble constant, a measure of the universe's expansion rate. It's a simple concept. For every megaparsec, about 3.26 million light-years, a galaxy is from us. It moves away at a certain speed. The tricky part isn't finding how fast a galaxy is moving, that's done by measuring its redshift. The real challenge is measuring the vast distances to these galaxies. That's where Cepheid variables come in handy. These stars have a consistent pattern of brightening and dimming, which correlates with their true brightness. In the early 20th century, Henrietta Swan Leavitt studied these stars and found a key relationship between their pulsation periods and luminosity. The longer a Cepheid star's pulse, the brighter it is. To gauge a galaxy's distance, you start by observing these stellar pulses. The next step is to compare the star's true brightness with how bright it appears from Earth, its apparent brightness. If a Cepheid appears to have a brightness of 24, it's incredibly faint, 16 million times fainter than the dimmest star visible to the naked eye. The final thing is the relationship between brightness and distance. Using the distance modulus equation, a fundamental astrophysical formula, astronomers can calculate how far away the star is. While Cepheids are cosmic lighthouses for tens of megaparsecs, Type 1 supernovae serve as beacons for hundreds of megaparsecs. Sometimes astronomers use both to double-check their cosmic measurements. With sophisticated technology, they've estimated the universe's expansion rate at about 73.4 kilometers per second per megaparsec using Cepheid variables. As astronomers awaited clarity from the James Webb Space Telescope, they faced a challenge. Cepheid variables often cluster with other stars, complicating brightness measurements. One such star, spotted in NGC 5584, exemplifies this issue, its light mingling with neighbors in Hubble Space Telescope images. The quest to resolve the Hubble tension continues, with the cosmos keeping its secrets just a little longer. The James Webb Space Telescope, with its advanced infrared vision, has brought into sharp focus Cepheid variable stars that were once lost in the stellar crowd. Observations of these stars in two galaxies, NGC 4258 and NGC 5584, have been pivotal. NGC 4258 is a well-measured neighbor, while NGC 5584 is further away, known for hosting the supernova SN1A 2007 AF. Over 320 Cepheid stars in these galaxies were studied using both the Hubble and Webb telescopes. The Webb's images, distinct and clear, stand out against the Hubble's more congested views. This clarity is celebrated in the study titled "Crowded No More," highlighting the Webb's ability to distinguish individual stars amidst the galactic throng. The research compared the period-magnitude relationship for both galaxies, with the Webb's data points in red showing a tighter, more consistent trend than those from the Hubble. This precision has led to a reaffirmation of the Hubble tension, ruling out measurement errors and pointing towards a deeper cosmic conundrum. The confirmation of the Hubble tension by the Webb telescope suggests that our current cosmological models, including the lambda cold dark matter model, might need re-evaluation. It also beckons a closer look at dark energy, which is thought to drive the universe's accelerated expansion and comprises most of the cosmos. Resolving the Hubble tension is not just academic, it's a quest to foresee the universe's ultimate fate. Will it expand forever, collapse, or tear apart? To find answers, astronomers are turning to new methods, like studying gravitational waves from black holes or the helium flash of red giant stars, to measure cosmic expansion more accurately. As the Hubble tension escalates, it opens up new field for profound cosmic insights. And with the Webb telescope's recent discovery of the most distant black hole, we stand on the brink of even more astonishing revelations about our universe. So get in touch with Infotech Science and also subscribe it.